welcome back. In the previous what we were discussing is the paradigm of clustering, where we said that there is a massive amount of data that is available, and in order to work over, in order to analyze it either by a human expert or by a machine or because of any other kind of requirement that the system may have, we said that we'll have to apply something known as clustering, and we saw two algorithms. One was the k-means clustering, in which using an iterative approach the cluster centers get moving, and the fuzzy Siemens clustering, in which the same algorithm was applied, but we said that every element belongs to every cluster by some membership degree, and we saw how these two algorithms operated. Now, one thing that both these algorithms are iterative in nature. By iterative, we say that as you keep on iterating, the solution will keep getting better and better and better. And of course, after a threshold, we need to stop. That threshold is normally defined by a human. That threshold is normally predefined into the system. Now, in both these algorithms, one thing that we kept was that the number of clusters were constant, they were specified beforehand. Now, ideally, this might become a big problem. Now, ideally, when you say that please cluster my data, give me some interesting amounts of data, you do not know how many interesting data you require. You may underestimate this number, you may overestimate this number. And both underestimation and overestimation of the number of clusters may eventually be wrong. If you underestimate some very interesting amount of data, may either not be visible, or its effect may not be visible. You will get some mean kind of thing over there. Another thing, that if you overestimate, you might get redundant cluster centers. So both of these are wrong. Now we've again got in numerous clustering techniques that we will not be discussing over here. The motivation behind discussion of clustering was only to get an idea, because we are writing in references further into the course. The subtractive Siemens clustering is another very famous cluster technique used that goes about how the cluster centers are improving, and based on that it can even tell you about the cluster centers that need to be there. You need not specify it up at start. Now, one of the problem with clustering is again that the data is highly massive. Your k-means and your c-means, with the iterative nature, iterating over and over again, may not be able to work at all in this because of such large amount of data that can even span across multiple disks. So we've got multiple techniques that are used. So the entire paradigm of clustering, I can always say that there can be some tree-based approach, there can be some density-based approach, and of course there are so many other approaches. What these would do is that you might have a top-down approach, so you kind of divide the entire data into clusters. So you get a hierarchical representation of clusters in such an approach, where every big cluster is broken down into some subclusters, the subcluster is broken down again into some subclusters. There will be that they can be opposite, that every you try to cluster out the data, making one subcluster. You try to cluster the entire subcluster, getting a little bigger cluster. You group them up into more bigger clusters. So breaking and forming high abstraction, low abstraction, there are wonderful things that are done with clustering. There are various iterative approaches towards the same. We will not be dealing with them. Again, what comes up from one of our own publication is that you had this cluster center C1, C2, C3, C4. What we said was that these are kind of parameters that we need to control. We embedded them inside we embedded them inside the system. We embedded all the centers inside the state, gave it to a genetic algorithm. And whenever you give anything to the genetic algorithm tries to try all combinations of it. It tries to find out all the various sort of combinations from it, and it asks you what is to be optimized. So based on that, using genetic algorithms, we try to optimize the number of data points in a cluster. We try to optimize the distance metric that was more or less presented, the unique distance metric, and all those sorts of things. So there are wonderful things that you can do with the entire paradigm of clustering. Much of it we'll not be kind of dealing with right now. Much of it we'll not be dealing out in this lecture series. So we'll move up into what is exactly the agenda for this hour of study. We'll move into again what are the basic types of problems that we are trying to solve. We'll have a look at it at the introductory and we'll take a little bit deeper into it, and once we've done with this, we'll straight away start off with the soft computing tools and techniques that we have been promising for now. We'll start off with the neural network, the genetic algorithm, and the fuzzy systems, and the hybrid systems at a much later point of time. So we'll be basically dealing with three kinds of problem at this stage. We'll be dealing with a function prediction problem. We'll be dealing with a classification problem, and we'll be dealing with an optimization problem. These are the three things that we would study as of now. The function prediction, the classification, and the optimization. The motivation of it was something that we gave it at the introductory hour. Now into our entire paradigm of discussion, when we were discussing the expert systems, the inputs and the outputs, the kind of modeling of the system, what was emphasized upon is that if I give a database to a kind of system, if I give a database to a soft computing tool, it should be able to find out some kind of patterns into it. Sorry, some bit of technical disturbance. Okay, so what we were discussing is that if I give in some kind of database to the system, it should be able to find out some kind of function that maps the inputs to the outputs. What we further discussed was that I already have a set of inputs and set of outputs. Now let me say that my problem is again that an input space needs to be mapped to an output space by this function. The problem of finding out this function is known as the problem of functional prediction. Right now, I'll assume that the input was in form of multiple points that are in my database. So there will be serial 1, 2, 3, 4, 5, 6 up to some big number n over here. There will be attributes 1, attribute 2, attribute 3, attribute 4, attribute 5, and so on till attribute n over here. And I'll assume there is a single output O1. Of course, the problem of having multiple outputs O2, O3, O4, O5, O6 can be decomposed into individual problem where one problem is to find O1, the second problem is to find O2, the third problem is to find O3. So I'm taking a single output case now, but that does not mean I'm taking any kind of assumption, because if there are more than two outputs, I'll proceed separately with each one of these outputs only for this discussion right now. So like this, I've got a big table with me of inputs and outputs, and I need to find out this function. What I eventually do is I first of all make it a space where my output is plotted at the vertical axis, and all my inputs A1, A2, there will be a space A3, there will be an A4, there will be an A5 up to AN, they are plotted in this space. So you can have a look at it that I am trying to plot a n plus one dimensional space in which the vertical axis represents the function value and the base of it represents an input that has been given. The vertical axis represents the output, and the vertical base of it, the base will be again a space or a surface that represents the kind of inputs that are given. It is ideally not possible to draw anything more than a 2D for me. I'll see if I can draw a 3D. So let me say I only take it A1, A2, A3, A4 are embedded somewhere inside this board. Now any point that I am given in this space, in my table over there, I have nothing but a set of input values I1, I2, I3 and so on up till In, and the corresponding output OI. This is what I've already got. So I move up to a surface. For every element over there, I try to find out where that input is located at that surface. I go towards the output and I plot this as a point. Now what this represents is one data point available for me from my historical database. This is what is the output of that data point, and this is what would be the value of the first attribute of this data point. So this will be I1, this will be some I2 and so on. What I get is that each and every point of that database can be marked in this n+1 dimensional space. So all I have is points like this. All I have are some points like this. One point representing one entry in that entire historical database. Now I mentioned the fact that all my inputs and outputs, whenever I'm trying to give a database to a system and to try to find out the function, they need to be bound. So I got this as a bound space. All my inputs and outputs lie between some A1 min and A1 max, A2 min and A2 max, and mostly an O1 min and an O1 max. I'll unfortunately make this assumption that my entire space that I plotted is not an unbound state, it's a bound state. The minimum of all represents the origin. Now what functional prediction problem are supposed to do is to try to find out this function that best fits these points. Is to try to find out a function that best fits these points. Now there are numerous regression techniques that can be applied towards this. So suppose I do a linear regression, it will give me this kind of a function. Let me approximately plot it up. This would be what will be the output of linear regression, and the linear regression is something very simple to do. You just say output is some function of inputs. So you simply say my control points are nothing but you regress inputs along with the plotted output, and any regression fundamental would be able to give you some set of parameters, and the output being of course a linear combination of input if it's a linear regression, or a quadratic if it's a quadratic kind of a regression. My quadratic regression would again be a much better graph. But what I eventually find out is that the error is too much. What I eventually find out is that the error is too much, because had this been the function to be predicted, for my first data this is the error, for my second data this is the error, for my third data this is the error, for my fourth data this is the error, the fifth is almost fine, the sixth is almost fine, the seventh this is the error, the third this is the error, the fourth this one is the error. So there is a bit of error over here, that's prevalent. The quadratic is much less in number. The quadratic kind of regression, if I apply, the error is reduced. So basically my attempt is, if I can kind of plot out this function, it will go over here, it will try to go up over here. Now you see it's something very difficult to plot this up. That is, I have given some random data, so it's very difficult to connect this up over a graph. It is very difficult to make a plot that fits in each one of these cases. That is because the points are randomly drawn. If I draw much better points over here in this search space, if I draw points like this, as it can be guessed, it is very easy to have any structure like this. It is very easy to construct this curve, and this is the function that we are trying to predict using any technique, neural network being one of them. There are numerous statistical techniques that will give you tools of doing this. So in our entire paradigm of neural network construction, the motivation would be, can we draw upon this curve? Now one thing you can notice is that they would have many curves possible. A curve would have been better if I had drawn it maybe like this, that I eventually did not draw. The reason is that all my data over here is assumed to be noisy. It is known that there is some amount of noise. So this point can actually have slightly better output, slightly lower output. It can have slightly lesser value of A1, slightly more value of A1, slightly lesser value of A2, slightly more value of A2. This can point about anywhere depending on what is the error in the input, recording of the inputs and the outputs. Now when it comes to historical database, all the inputs and all the outputs have been recorded independently. So if it's that you're trying to make a function that tries to find out what is the humidity at any point of time, and you know the humidity depends on 5 weather characteristics, 5 weather parameters. So when you're making the historical database, you measure each one of these attributes and the corresponding humidity independently by all the instruments, and the instruments are always thought to be erroneous. So depending on that, there can be slight deviations in the point depending on what is the error. Sometimes there are human errors. So their reading was 25.8 and I had that to be let's say 82.9. So this point will be, in place of being here, it will be somewhere here. Now it does not mean I'll make my curve like this because this is noisy. The actual curve will be like this. So whenever I'm making this kind of curve, I need to be rest assured that my error has some kind of noise. Of course, if you can take uncertainty into the picture, that some data is completely unavailable, then that would be even better. It would make an even good system. Of course, many times when there is uncertainty, we try to fill in some average value, we try to find out some close correlation with some elements and try to fill in values that are close enough to that. Many times we try to analyze what is the trend of that behavior and we try to fill in values. That is how we normally deal with completely missing data, complete uncertainty. But here the point is only if it can, and the function prediction problem, only if I can draw this kind of curve. Now it looks a very simple problem. And of course, I use a hiring technique known as neural networks or something else to draw this kind of curve. But what eventually comes out is numerous problems. Sometimes the data is very less. So when you got too few data items, it's very difficult to construct something. Sometimes the dimensions are very high. Now what you are viewing as a complete 2D picture over here, what you are viewing as a complete 2D picture over here is actually a very complex curve that spans across dimensions, and whenever it comes across dimensions, every technique becomes very computationally expensive. Sometimes the degree of noise is very high, so it's like you do not know, every element can span across not many areas, and this you already know, so you need to do something in your system that noise is accounted for. So what the basic intention is that even drawing of this curve by an automated technique is a difficult problem. Another problem we normally face is that you do not know what is the complexity of this curve. Sometimes the problem are very difficult, so lines would come out to be like this. Sometimes if the complexity is very low, it would come out to be a sweet little curve like this, and the complexity can change it. For most of the discussion, the complexity may be defined as the number of terms over here and the number of terms over here. So regarding all this, one of my problem would be that can I draw this curve once I am given this point, can I reverse this curve out there? Of course, towards the later section we will see how the neural networks do solve such kind of problem, which would be the next topic of discussion. Now once I devise a mechanism that is able to draw a curve, I get a very good functionality that is already there embedded into the system now. The functionality that I get is that given any database, I'll be converted into a function. So I'll be able to extract out some kind of information from that system. I'll try to extract out some kind of knowledge from that system. Knowledge being represented by all the parameters of that curve. Because different techniques may assume different types of techniques may have different types of representation of the curve. Whichever format I represent the curve, whichever way I represent the curve, the characteristics, the parameters of that curve is nothing but the knowledge base that we have been talking about. The other problem is called as the classification problem. We had an extensive discussion over this kind of problem when we took up things like the problem of matching of a face from a face in the historical database. So let's see what we had an extensive discussion where we said that what are the anomalies involved, what are the uncertainties involved, all the possibilities of noise involved. We had an extensive discussion over it. Now this is a problem of classification where my output is one of the persons out of all the possible persons. And sometimes of course if there's a many class classification problem, then I need to decide whether this class is present or not. That's when an output can be mapped to multiple classes. Most of the problem we deal with are single classification problem, in which my output is one of the classes possible. So here what I said was that we had a concept of feature that I would from now on call as an attribute, and I said all set of features uniquely identify the person. That is what I made it I mentioned there. Some of which were what possibly that features can be solved. Some of it we'll be seeing at the later case codes of this, so we'll be taking specific applications of this from the domains of biometrics and biomedical engineering. But I say that a feature set completely defines a person, a feature set completely defines a class. Whenever the same feature set is there, the same class is bound to exist. So what I say that my system again has a set of input and a set of output in the form of table. So there will be 1, 2, 3, 4, 5, 6, 7. There will be attributes over here up to an. There will be output over here. I again assume only one of the outputs. They are all real value numbers, but outputs are in the form of A, B, C, D and E. Saying this person A, this person B, this person C, this person D and this person E. And there will be again multiple A's over here. There will be multiple B's over here and so on. There will be multiple C's over here. This is what my database is. I do exactly the same thing that I had done for the functional prediction problem. I do exactly the same thing. I plot an n-dimensional space. So let's say this was A1 and this is A2. Then I have taken the output value as the vertical axis. In this case I have taken I'm not plotting the output value because since it is a label and labels cannot be plotted. They cannot be assigned numeric equivalents. So it cannot be plotted, so I have not taken any vertical class as the output axis. In place of that, what I do, I draw an n-dimensional space, so there will be some A3, there will be some A4, there will be some AN. I plot it up, I take in each and every element of that recording, that database, that set, and I say I plot it in this curve. Now based on all the inputs, once I get all the inputs, I can have some value of A1, A2, A3, I get it as a point over here. I look at the output and I say that this was point A, so I write A over here. Similarly for the other classes I do. Here there will be some B, here there will be some C, here there may be some more C, here there may be some D. There would be some E over here. And there will be of course some A over here. Now because I cannot visualize more than 2 degrees, I'll just rub this up and that this exists. So there's a multi-dimensional space drawn over here at this board. I'm only showing its 2 axes. Of course my inputs and outputs are bound. In this case the outputs are naturally a finite set and the inputs are bound. Now one thing that you can already notice is that all A's are together, all B's are together, all C's are together, all D's are together. That is because of again assumption that I had taken out in that place. What I said was that the combined value of parameter in features, the combined value of attributes, they uniquely identify a person. So whenever the same input comes again, the class needs to be same as from my historic database. Whenever this set of attribute values would become, my class needs to be the same. Again, what I have said is that any type of features, it can have some bit of noise. So might be when the photograph of person A was taken, this was its position in the feature space. By the way, this can be known as a feature space since we are dealing with the word feature. In that case, it would be an output space since we have plotted the output. What the space block before would be called as the output space, here it can be called as a feature space. So inside this feature space, if there was a little bit of error in measuring A2, my point would lie here. If there was a little bit of error in measuring A1, my point would lie here. What I again said was that for two classes, the feature value need to change as large as possible, and therefore it can be seen that when I measured D from A, my value of A2 changed largely. My value of A1 of course did not change largely, but the value of change of A2 was large enough. So it's like two people had the same distance between the eyes, but they did not have the same, but they were well apart when it comes to the circumference of the face. So based on one parameter, the distances became very large. The problem of classification is whether I can try to form these decision boundaries that separate one class from the other. The problem of classification is whether I can formulate some kind of decision boundaries that separate one class from the other. Now of course, from this very example you can see that there are multiple decision boundaries that can be formed. I could have this line in place of this like this. I could have line in place of this like this. They are all separating the classes. What my system is supposed to do, it is supposed to predict these decision boundaries. Unless we know that whenever the next occurrence of A comes, that will be somewhere very near to this. Whenever next occurrence of E comes, that will be somewhere very near to this. So I can give the correct output based on these decision boundaries whenever they have been formulated. Now again, it can be seen clustering is one of the fundamental factors by which this thing can be done. Clustering is one of the mechanisms by which we can have this kind of class being done. Now when we were dealing with the problem of functional prediction, we said that there is a possibility of large amount of noise. Noise can vary anywhere between small to large. And of course, when it comes to functional prediction problem, a large noise means that your system needs to have some mechanism to handle that noise. When it comes towards classification problem, the parameters that I take for classification may not be ideal. Ideal parameters have got too less distance between elements of the same class and too large distance between elements of different class. So I can say this distance needs to be as small as possible and this distance needs to be as close as possible. These distances are known as the inter-class separation that would normally be defined by as summation of the norm between an input I and an input J such that I and J belong to a class C and of course because we have two distances I and J and I being added up two times, sometimes it would be wise to take either I, J is greater than I, or sometimes it would be advisable that if you divide this factor by 2 and this we sum it over all classes C. So this is what would be my intra-class separation, the separation between elements of the same class. So I add up all the separation out over here, I add all the separation out over here, I add all the separation out here, I add all the separation out here, I add all the separation out here. Between these two, between these two, between these two, between these two, here between these two, these two, these two, these two, and so on. This number needs to be as less as possible. And my intra-class separation needs to be as high as possible. So my intra-class separation would be probably that I sum up an input I and an input J such that I and J do not belong to the same class. So let's say I belongs to a class C1 and J belongs to a class C2 and C1 is not equal to C2. I add it up over all classes, over all combination of classes C1 and C2, and this becomes my inter-class separation, which needs to be as large as possible. And just to divide it by the total number of combination of elements, I'll have to divide it by all combination of elements possible over here and over here. All the combination that I have added, I'll have to divide by the number over here, over here. So this needs to be as less as possible, this will be as large as possible. My system is very easy to classify if my intra-class separation is very less and my inter-class separation is very high. Because as it was the system, I could have drawn the boundaries multiple times. I would have drawn the boundaries in a very flexible way. There was not much constraint. As we shall see in the next example that I take, usually there are constraints. So my ease of classification is nothing but my intra-class separation divided by my inter-class separation. The less this number be, the more easy it is to classify. The lesser this value, the more easy it is to classify. And hence, even before you are making in some kind of database, you are there making some kind of, doing some kind of system, it would be sometimes be advisable to measure these metrics and try to find out that how easy is it to even make a system out of it. I'll rub out this space. What I'll draw is I'll draw something new. Let me take only two classes here, X and O, and let me say my classes in the feature space are here. Let me say these are my classes. Now I cannot draw any decision boundary. Let me say I draw it like this. This has been identified wrong. This has been identified wrong. If I draw it up like this, this has been identified wrong. So the classes are intermingling with each other. So it's very difficult to draw the boundaries. And I cannot have a classifier that will give me 100% accuracy in this case, apart from the fact that I make this type of classification. But then again, this can be possibly, even here, this would be wrong. So by 100% accuracy would be if I draw this. But again, this can be a noise either due to wrong measurement of classes, either due to wrong instruments, or due to anything in this feature space that has feature 1 and feature 2. And if I make this kind of system, the possibilities are that any class over here, if this would have actually been X, all these values here would have been wrongly predicted. So what these kind of problems exist? When the classes start intermingling with each other, it is very difficult to draw this decision boundary. So there are three decision boundaries, I say D1, D2 and D3. This is a problem of overfitting, where I very adamantly try to separate out classes by a curve. It should be avoided because of the possibilities of noise that your system does not. This would ideally be called as underfitting, where I try to make a too simple system. I try to draw a line that would separate. And this is the ideal fit that we are supposed to find out. Similarly, in a function prediction problem, if I make in a system like this to fit this kind of data, if I make out this system and if I make out this system, this would be called as an overfit, this would be called as an ideal fit, and this would be called as an underfit. And of course, we do not know in our automated system what is the ideal case. The ideal is very easy to draw on the board. Whenever you are given something, but on a practical system that spans across so many dimensions that you cannot even see, it is very difficult to say whether something is overfitted or is it that something has underfitted. It would be eventually very possible to make that out. Now, these are two interesting problems. One says of classification in this case and one of function prediction in this case. If I delete an attribute over here, A3, let's say there was an A3 over here, I completely delete it vertically in my database table. If I am able to classify this space without use of an attribute A3, then also I have a perfect system available. I'll have a perfect system available that is able to give me the correct output without the attribute A3. Well, let's say I could have deleted A4. In classification, all I need to do is that a view must exist whichever way I view it. Whichever there is a hypercube kind of thing, there is a complete space, I can change it across multiple dimensions, I can have multiple views, combination of A1, A2 and A3 or A3, A3, A4 and A5. I can have multiple dimensions. If there is space that I clearly classify any one of these classes, then my task is done. So let's say the same A1, A2 fundamental in which the classes were very distinct with each other, I add up an A5 over here and I draw the space called as between A5 now and A1 now, and it comes out to be like this. The X and O that were very difficult to find out here, they come out to be well distinct. That is like I'm adding up a space over, I'm plotting up the space vertically, all these go up and all these go down. The classification is easy to learn. So addition of an axis in the classification problem, addition of an attribute, it has a lot of meaning. It is very easy to classify, but it makes the problem more complex where the dimensionality increases. What is eventually known as the problem of curse of dimensionality. My computation exponentially rises when I increase a dimension. If I increase a dimension in classification problem, it is very easy to classify. And therefore, whichever classification problem that you take, whichever classification problem that you may work with, it will be advisable to have as less attributes as possible as long as you can classify with high accuracy. It will be good to take in the number of attributes as less as possible to save from unnecessary computation, unnecessary workload. But of course, if you cannot classify, you have to add more dimensions. You will have to add more attributes into your system. Another thing that is usually said in case of a classification problem is that if under any view of this problem, I was not able to clearly distinguish between X and O. I tried all views between A1, A2, A3, A4, A5, with the problem has 5 attributes. I wasn't able to separate out these two classes. They were still intermingling with each other. The accuracy rate, that's why was low. What is it that I try to add in attributes? The thing that I had to do is that I had to add in good attributes to the system. Now, how is goodness of that attribute defined? How is it that we say that what is it that will add goodness to this solution? One thing, of course, we can do is that we say that we add an attribute to a system that will decrease the interclass separation and that will increase the interclass separation and that will decrease the interclass separation. But then what if it makes addition of a new attribute I6, it makes this go vertically up in this board, it makes this go vertically down in this board, it does not affect this. It does not at all affect these regions. My attribute A6 is useless. I have unnecessarily added new dimension, new complexity. So for any classification problem from this feature space, it is very difficult to find out what is it that I need to give as attributes. Again, consider the problem of face recognition. Suppose I am taking the problem of face recognition, and what I do is that I take the length between the eyes, the circumference, and so many different kinds of parameters. The parameter list becomes heavy. If the parameter list is heavy, then the associated problem is of course the problem of curse of dimensionality. If the associated problem is curse of dimensionality, that means because of attributes, all my algorithm is to do, it has to perform a lot of computation. My learning will become very slow. Because of slow learning, I have to stop my learning algorithm early so that it gives results in finite time. My data requirement will be very heavy. My training data size needs to be very heavy. Why it needs to be heavy? Because in a multi-dimensional feature space with maximum attributes, a new hyperplane has been added. Now the curve that I make, it needs to be flexible enough. The curve needs to be flexible enough, so therefore the data requirements increase. And so many problems that arise because of dimensionality. For the same problem of classification, selection of good features for the face, I cannot measure the goodness of every parameter and say that I have taken the best set of parameter. Let's say only my distance between the eyes, my circumference of the face, and my width of the lips, they were very good parameters. I measured it from the space. But I cannot say that whether this combination is best, because what it might be having is points across the decision boundaries, they might not be affected with by this. Taking in some different combination might work better. So selection of the correct combination of parameters in this classification problem is itself a very big problem that we normally deal with. This is the famous problem as soon as the problem of feature selection, when you got some set of attributes available. Another problem that happens in classification is the problem of having fairly low data. That is when the data has not been very diverse apart. I had taken photographs of people from the same angle, from everything was same. I clicked it 20 times. I got in this as person A. So there are some 20 over here. I clicked it for person B. I got this data. They were clicked exactly with the good cameras. They were clicked exactly as it is. They were clicked consecutively. There was no change of curves, equation, background, nothing. But when the other time the user goes, takes rest, comes back again, now things have slightly changed. The camera orientation has changed, the pixels have slightly changed, everything has changed. Now I get this as my recording. Now I do not know whether it belongs to A or it belongs to B, because my algorithm could have given me this decision boundary, it 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 could have given me this decision boundary. It's very easy to formulate decision boundaries. So that's again a problem when it comes to classification problem. Now I do not know what does this correspond to. It corresponds to A, it corresponds to B. One problem may be, of course, that the recording data has very low variation. The other problem may be that there was an abrupt noise. But then again, the way to solve this problem is, of course, to take in high amount of data. This problem can be handled when the data is fairly low. When it comes to function prediction problem, we have an interesting case is that you cannot necessarily drop in attributes. It says my output depends on 5 parameters and then only 4 of them. Now the introduction of the 5th parameter may change the output anytime. So that's not unlike the classification problem where the attribute taking and attribute deletion is fairly simple. In fact, that again puts up a very heavy constraint that all the things that sufficiently change the output need to be known for any function prediction problem. It needs to be known that how the output is changed when these inputs are changed. If you do not know any input, if there is anything external that is changing the output of the system, then you cannot make it a system, or you have to assume that in whatever data you record, either at the practical time when the system is deployed or at the time in which your database is recorded, the value of that parameter is fairly constant it does not affect the output much. Of course, for most of the problem that we solve in real life application, it says that we try to guess in the inputs. We try to guess in what the inputs are going to be for any kind of function prediction problems. But again, it is assumed that taking more inputs would either mean that the new inputs that we take, they are quite similar to inputs already there. So it's like if we take it an A7 in which we have A5, we already say that A7 can be A1 plus A2 plus 7 times A7, so in some relation, so correlation will be very high. Or we say that whenever we take in some new parameter in this problem, it behaves fairly passive in nature, so it does not really change. So that's like other parameter changing drastically and this parameter is almost like constant in nature. Or of course that the output does not heavily depend on this parameter. The output even for large changes in this parameter, there are very small changes in the output, so you can always neglect it up. The last problem of course of study is the optimization problem. Here we have a system that has a set of controllable parameters C1, C2, C3, C4, C5 up to Cn. We need to find out the most ideal values of Cn where any Ci can lie between an upper bound and a lower bound. Between a lower bound and an upper bound. This is known as the functional value. I'll denote this by f. This is known as the value that needs to be optimized, and my aim is to minimize f or maximize f. Here I will not take the case of maximization of f as it's exactly opposite to minimization. Maximize f ultimately means you minimize minus f. So with a little introduction of a minus sign, everything can change. This is what is known as the problem of optimization. That given the set of control points in which I can, of course I use more often the word system than a function because ultimately we deal with real life systems. A system can be controlled by these control points, each of them lying between an upper bound and lower bound. I need to find out the least value of f for any combination of values. Again, I plot a highly dimensional space. I plot C2 here, I have C1 over here, and I plot f over here. So I try out all these combinations of C1, C2, C3, C4 and make it a surface. I make it this kind of surface. F is the vertical axis, C1, C2 are all the base of it. Now it's very easy to say I plotted this surface, but it's practically impossible because all the combination of CIs for all the at any resolution, at any decent resolution, plotting all the combination of CIs would need intensive calculation. Sometimes calculate this f takes a lot of time to compute. There is a complex relationship using which this f needs to be calculated, and as a result calculation of this f is very slow. So you can maybe only try to find out some 14 to 15 values and 2 hours or over. It might take in 25 minutes to calculate any one combination of CIs. Or of course, sometimes the n can go up to 120 or 150. So you can well understand the combination. If I divide this up into 100 values as well, then that will be C1 can change between from anywhere within the 100 range. I am taking a resolution of 1 by 100, and that will be 100 raised to power 120. So that will be intensive calculation that you cannot even think of counting. The aim is to find out this. The aim is to somehow find out this point in an optimization problem. Once I found out this problem, I can very easily say that this point was the optimal value of parameter 2, this was the optimal parameter of parameter 1, and f of O1, O2, O3 up to On was the final value that my system should have given. This is the most optimal value. So basically the intention is to calculate f the least value of this function. Now here we've gotten a concept of local minima and of a global minima. A local minima is defined by any point in this high dimensional space that has a lower function value than any of its near neighbors. All these are nothing but local minimas. They have got smaller value as compared to anything. If I am dealing with the problem, I was dealing with the problem of men, that I will take it for this entire series. If I had taken a problem of mass, I would have this as the global, as the local maxima, this as the local maxima, this as the local maxima, this as the local maxima, and this as the local maxima. Now, global minima is one amongst all the local minima that has least value of them all. Global minima is one amongst all that has got the least value. Now usually a problem may have multiple local minima, but it may usually have a single global minima. It rarely happens that two points have exactly the same global minima unless there is some kind of redundancy in the problem representation. It might not happen that a system has global minima, but the aim is to find out this global minima. Now, why do we talk about the local and global minima? It is because of one simple fact. Many of the techniques we used, many of the statistical technique we use, again, optimization is a very famous problem of statistics. People must have, everyone must have dealt with it in some or the other format. What most techniques they try to do is that many of these statistical technique, they generate a random combination of C1, C2, C3, C4, C5. That will be again a point at this place. They try to find out this gradient and they try to make this point modified in such a way it moves towards this gradient. So this is how it moves. And here it's stuck. And then they do something that will try to save this point from the local minima and it will try to pop it up somewhere. So that's the main reason why we say that we discuss a lot about the problem of local minima and the global minima. Again, not the case that only the gradient approaches are bound to stuck in local minima. The statisticians have been using this gradient thing for very long. Until it came up to genetic algorithm that we'll see was a much better approach that saves from all the local minima. We'll be dealing with how this happens. But again, any optimization technique, be it a multi-agent system, be it a gradient-based approach, is prone to get stuck at a local minima, and it is likely to give result at a local minima than at a global minima. And of course, when we deal with the problem of optimization, the point is to get this global minima. Now, one thing again that we need to consider, that the space is highly dimensional in nature. Complexity would again be defined by the number of hills and valleys over here. So if they are 1, 2, 3, 4, 5, 6, 7, 8, 9, by some view there are so many hills and valleys, it's a very complex problem. Complexity of a functional prediction problem was again by the number of terms. Complexity of classification problem was by the ease in which the separability can be maintained. Complexity of this problem would be the number of hills and valleys. And then it comes to really complex problem, that is how we'll see that genetic algorithm emerge out to be the solution to solve these kinds of problems. So the intention is basically if we can get this global minima, for which of course we would be using some genetic algorithms and some evolutionary techniques that we'll be seeing towards the later stage of the course. So mainly this was about the optimization problem. In all these three problems, classification, optimization and function prediction, we got a lot of statistical techniques, but all these statistical techniques have some limitation that And in order to solve them, we need some soft computing techniques that we'll see from the next lecture onwards. We'll see as how these statistical techniques, they are prone to some kind of limitations. In neural network, we saw that the regression failed. In this optimization, we said that the gradient approach may not be refined enough. In classification also, the approach, they mainly try to draw on boundaries. Now there is a limitation in how this function can be by the statistical approaches. There are some limitations. There are some probability-based approaches that they use that again have some kind of limitations. That we'll see, and we'll try to use soft computing techniques in order to overcome all these limitations. So basically from the next lecture onwards, what the motivation would be in understanding all that is the limitations of the individual learning techniques of the statistics, and hence we require some basic soft computing tools. Now again, one point should be clear from now on, that the basic motivation has already been set up. So any real life application that you get, you can model it up as a standard problem of soft computing. And the thing left to be done is that in how we model up these tools, in how we can use these tools, and to look deep insight into these tools as problem solving agents. From next class, we would be discussing about the entire paradigm of the neural networks. We'll look up a little bit more into classification, but that is right towards the end of the neural network, and immediately would follow the usually computing, the basic genetic algorithm first, and then the fuzzy logic, and then we'll proceed up with some